Last week, we explored how electromagnets made for better sounding records. By using a phonograph cartridge to both make and play back records, much better sound quality was attainable through the now venerable disc. But electromagnets were far from finished showing off their awesomeness. As we learned more about what we could do with the electrical signal provided to us by microphones, we started to put electromagnets to a very different use: magnetic recording. I'm Alec, and this is Technology Connections. As is often the case for technological progress, tracing its history can be a bit complicated. The first magnetic recording device was invented by Valdemar Poulsen in the late 1890s. He received a patent for his design in 1900. Why haven't we talked about this before? Well, the simplest answer is that while his invention was early, it was never really put to use, especially not in the use of audio recording. Let's go through the original design though, just for kicks. He who must not be named invention was originally designed to be a dictation machine or a telegraph recorder. Called the telegraphone, it used a funny method of recording. It exploited a property of metals that could be magnetized. Here's what I mean. If some metals like iron and steel are exposed to a substantially strong magnetic field, the field will actually cause the metal itself to become slightly magnetic. This is called magnetization. It's useful in many applications. One you may have encountered is the common screwdriver. Screwdrivers are often magnetized so that screws will stick to their tips. The wire recorder used a long, thin wire that sat in a special device fitted with an electromagnetic coil. When current was passed through this coil, it created a magnetic field, just like in a loudspeaker's voice coil. But this coil was arranged so that the field it generated would be transferred into the wire. The wire was made of steel, which is a metal that can be magnetized. So as a current was passed through the special device, the wire itself would become magnetized, but only in the spot that was right next to the device. The rest of the wire would remain unaffected, so what you'd end up with is a wire with a single blip in the middle that's magnetized. But say we run the wire past this special device at a decent speed. Then we could change the magnetization in the wire over time. Say we're recording a telegraph signal, and the signal goes like this. If we send current through the coil while we are getting a signal, and we move the wire past the coil at a steady speed, we'll end up with a wire that is magnetized in a pattern that matches that signal. Okay, but what good does this do? Well, as I'm sure you remember, electromagnets also work in reverse. Just like how a loudspeaker is the opposite of a microphone, and how a phonograph cartridge can either record or play back records, this device can also detect magnetization in the wire. If we were to run the wire back through the device, the varying magnetic fields now surrounding the magnetized wire will induce a current in the coil. We can use that current to see what's on the wire after it's recorded, and thus we can play back a message. The wire was also capable of recording audio, but again, it was only of sufficient quality to be a dictation machine, and hardly anyone ever used them, as the dictaphone, a phonograph-based dictation machine, was far more popular. Plus, this was before the days of amplification, so the signals recorded onto the wire were made using telephone-style carbon microphones and could only be heard with an earpiece. Fast forward 45 years and we're near the end of World War II. Now the wire recorder is in vogue again because we can now easily adapt the technology to be used with electronic amplification. Not much really changed with the wire recorder itself, except the wire got thinner and the special device, which by the way is called the head, was now powered by a triode vacuum tube, often using electronics from a radio. And when the wire was played back, the signal coming from the head was amplified by the same circuitry and sent to a loudspeaker. Let's have a look at some recording wire. This spool contains over a mile of wire. That may seem ridiculous, but it's absolutely true. This stuff is so tremendously thin that you can barely see it, and it has to be thin in order to be practical. This 7,200-foot spool can hold about an hour's worth of material, and when running the wire past the head at the relatively standard speed of 24 inches per second, you'd get 3,600 seconds, or 1 hour. But being so thin presented some obvious problems. This stuff is fragile, and that's putting it lightly. If it came off the spool and unwound, you'd have no chance of getting it back on. It would instantly tangle and become an unmanageable mess. But if it did break, and you were lucky enough to have all the wire safely secure on both ends, you could mend the break with a simple square knot. You might lose a bit of material at the repair, perhaps half a second or so, but the knot could go right through the head without trouble. Wire recorders only stuck around for a few years because magnetic tape recorders were right around the corner. Earlier tape recorders, such as the Blattner phone, used solid metal tape, but you're probably much more familiar with a tape recorder that uses a flexible plastic tape. The German magnetophone was the first such machine to do so, developed in the 1930s. Tape recorders work exactly the same as wire recorders, the only real difference is in the tape itself. Tape recorders were so much easier to use than wire recorders that the wire recorder almost instantly disappeared. So what is in magnetic tape? The answer might surprise you. It's rust. That's why it's brown. Magnetic tape is made of a plastic film backing that has a coating of iron oxide powder on one side. Iron oxide is literally rust, as it's the result of the oxidation of iron. Iron oxide is easy to magnetize, so it became the obvious choice for making tape. By using a fine powder, magnetic tape was able to run at much slower speeds than wire. This was because the fine particles were magnetized individually, and thus you could get changes in magnetization closer together on the tape. This was important for high-frequency signals, which need to alter the magnetic field on the tape very rapidly. With wire, they couldn't get too close together, so the wire had to run at the very fast 24 inches per second. But tape only needed to go at 7.5 or even 3 3/4 inches per second to get the same quality of sound. Let's go into that a little deeper. Recording wire is a solid metal object, and because of this, when you magnetize one spot on it, the magnetization will sort of bleed into the areas next to it. That meant that the definition, that is the fineness of the points we can magnetize, is very large. So in a 24-inch section of wire, we can only effectively change the polarization of the field maybe 10,000 times. That may seem like a lot, but it means that we're limited to recording sounds up to that frequency, since these 10,000 changes will pass the head in 1 second, resulting in a 10,000 Hz noise. Because of the physical limitations of the wire, we cannot record sounds any higher than this. If we slow down the speed to 12 inches per second, now we can only fit half the detail on the wire. So in this case, the most detail we can fit is 5,000 changes per second, or 5,000 Hz, because only half the wire goes past the head in the same period of time. What this means is that as you slow down the wire, the sound becomes muddier because we can't record higher frequencies. The slower the wire travels past the head, the less detail we can get on it. And that's why the wire is absurdly thin and long. The only way to have it sound any good is to have it move past the head very quickly, and thus the only way to get a sufficiently long recording time on the wire is to have it be very, very long. But tape was completely different. Because it uses a powder of iron oxide, there were small particles that could be magnetized on their own. If we were to zoom in really far on this tape, we'd see these microscopic particles. When a point was magnetized on the tape, only the particles directly under the coil would become magnetized. There was still some bleed of magnetization like in the wire, but much less, so we could pack far more detail into this tape. What took 24 inches of space on a wire only took a few inches, maybe 2 or 3 on the tape. This meant that tape only 1,200 feet long could record an hour of material with better sound quality than the wire. If we increase the speed, we could make the recording even better. Tape came on reels like this, and while it's bulkier than wire, it's a hell of a lot easier to deal with. It's nowhere near as fragile as wire, and being larger, it's easier to handle. Tape was better than wire in every conceivable way, except one. The particles of iron oxide that make tape so useful also produce a side effect: noise. Because of the randomness inherent to the particles, there was always a slight magnetic field left between them. Even on a completely blank tape, this randomness can be heard. It manifests as a hiss, and this is what we call tape noise. There would soon be ways to deal with this noise, but we'll explore them later. So let's look into what using this new tape was like. This is a Sony TC 366 tape recorder from 1970. It's a consumer model and thus it uses non-professional tape, but make no mistake, this machine records music with all the fidelity we expect today. But we'll talk about that later. Looking over the machine, you'll find lots of controls. It may look overwhelming, but once you understand how to use it, it makes perfect sense. The empty reel on the right is what's called the take-up reel. It takes up the tape after it passes the heads. A full reel of tape was placed on the left-hand side of the recorder, then it's threaded through the heads into the take-up reel. Speaking of the heads, let's take a look at those. Most machines like this have 3 heads. The tape first passes an erase head. This head is only enabled when recording, and its job is to record a very high frequency, past the limit of our hearing, and very strong signal onto the tape. This randomizes the magnetic field of the particles in the tape, and thus erases it. The second head is the record head. This one is also only used while recording, and it magnetizes the tape as it travels based upon the sound signal received by the tape deck. The third head is the playback head, and this head reads the sound recorded on the tape. Having 3 heads is not strictly necessary. Just like in a wire recorder, the record head could actually be used as a playback head. The tape heads work both ways, so really all we need is the erase head and a single record/playback head. But by having the playback head separate from the record head, you'd gain the advantage of being able to monitor your tape as you record it. These switches here change whether the headphones you're using are receiving the source you're recording or are receiving what's being picked up by the playback head. You'll hear it with a slight delay caused by the distance the tape has to travel between the heads, but it's an invaluable tool nonetheless because it allows you to monitor the actual record levels on the tape. Record levels? So here's something to keep in mind about tape. There is in fact a limit to how much we can magnetize it. Once we get past a certain threshold, it can't take any more volume and the recording will become distorted. To help you figure out how much you can put on the tape or how much you can saturate the tape are these level meters. They're usually marked VU or volume unit. The scale goes from -infinity to 0, and then we meet a red line. 0 is full saturation, and going higher than that pushes the boundaries of what you can record. With tape though, you can go into the red range slightly without noticeable distortion, so in general, you want the material recorded at or near 0 when it's at its loudest, with peaks hitting in the red zone only occasionally. There is no stopping in the red zone. You want the recording to be strong because otherwise you'll hear the noise in the background, but it can't be too strong or it will become distorted. So let's record some music on this tape so you can see what it looks and sounds like. First, we thread the tape we want to record onto. I have the source heading into the tape deck, and here we can see the level meters dancing to its volume. To record, we need to hold down these red tabs while we turn the selector to forward motion. That way it's pretty hard to accidentally record over a tape. I'm going to record it at the middle speed of 3 3/4 inches per second. So to start out, we want the level somewhere around here. We have 2 meters, by the way, because this tape deck records in stereo. Now that we're satisfied with that level, we can begin recording. But now, if we switch the monitor to tape, we'll find that we're not quite recording to the level we thought we were. Variation in the tape and machine can lead to this, and that's why having separate record and play heads is important. So now we can correct the level and we'll get an excellent recording. So what's going on now is the signal it's recording is being boosted by the amplifier in the tape deck and then sent to the record head. This is creating a rapidly fluctuating magnetic field right next to the tape. As the tape passes the heads, the field magnetizes the tape, but with a varying degree over time as the tape moves past it. So the tape becomes a linear representation of the strength of that signal over time. This is representing sound just like the wobbling groove of a phonograph record, only instead of using a physical medium, it's using a magnetic medium. As the newly recorded tape passes the playback head, the varying degree of magnetization as it passes it induces a current in the coil of the playhead, and the current is amplified and sent to both the headphones we're monitoring the recording with and the VU meters that visually show us the strength of the recording. So how does it sound? I'm recording music from YouTube's audio library. This is the source material I'm recording. Now we'll switch it to the tape. You'll hear it briefly repeat as we switch to the tape because of the time it takes the tape to travel from here to here. It doesn't sound that much different from the source, does it? Now, if I stop recording and switch to the fastest speed, you'll see it's even better. Again, here's the source. And now here's the tape. You might be amazed at the sound quality this thing is capable of, and I wouldn't blame you. We all tend to believe that everything is better these days, but we've actually had sound recording figured out for quite some time. Let me show you the problems that a bad record level causes. Here I've got recorded the tape way too soft, with the needles barely moving. If I boost the sound so you can actually hear it, you'll find that there's a ton of noise. That's the tape hiss, and the problem is that the signal we're recording is so weak that it's barely louder than the noise itself. Now if I record with the level too high, the sound starts to turn to garbage. This is what's called recording too hot, and while the sound is bad, it's a different sort of bad. It becomes really distorted. You might be surprised to learn that this tape actually has two sides. When you reach the end, you can unthread the tape, flip both reels over, and you have another side to record onto. This deck, as indeed many consumer decks at the time, records at 3 different speeds. The 2 faster ones are suited for music, at 7.5 inches per second or 30 centimeters for the rest of the world. A standard length tape will hold 30 minutes per side. At half the speed, you shouldn't be surprised to discover that it can record 60 minutes per side. And at the slowest speed of 1 7/8 inches per second, it can record 2 hours per side. But this speed sounds like garbage. Take a listen. This speed was mainly used to record speech or to make a very long recording where quality wasn't important. Since tape had 2 sides, eventually we had recorders that had a feature known as auto-reverse. These machines, like this Ampex, have 6 heads. 3 of them work in one direction, and the other 3 work in reverse. This machine is very high-end, but it's kind of a basket case. Its bias adjustment, which I'll explain what that is in a later episode, is all messed up, and thus it can't record. Also, there's a faulty switch for starting the tape, so you have to press this button to get around that. But it plays tapes fine, and its auto-reverse function still works. When it got to the end of a tape, it would simply reverse the direction of the tape and then switch to the other set of heads. You could either do it manually, like this, or if you recorded an auto-reversing signal onto the tape, the machine could do it automatically, like this. Auto-reverse was more or less a luxury feature, but it did improve the user experience. Perhaps the biggest change tape brought to recording music was editing. Before tape, if you wanted to edit different songs together into a program, you'd need multiple phonographs, a source switching mechanism, and a whole lot of patience. Also, editing mistakes was nearly impossible. If you screwed up a recording, you'd have to throw it out and start all over again. But with tape, you could physically cut out the section you wanted, or didn't want, and piece it together in what's called splicing. Also, professional tape decks could record 4, 8, or even 16 things all at once. Each recording was called a track, owing to the railroad track-like nature of having multiple recordings split along a single tape. These more elaborate recorders used multiple heads and very wide tape, and allowed for musicians to record different instruments and voices on separate tracks, which could then be adjusted individually in a process known as mixing. But before we get too carried away, let's just end with what tape brought us. We finally had high-fidelity, easy-to-use recording equipment, and the advent of multiple tracks brought the possibility of stereo into the home for the first time. Next week, we'll be exploring less of a technology and more of a concept. Our mission next week is to explore stereo sound and high fidelity.